Example 4, we're supposed to graph f of x equals log of x base 3. And if I consider f of x as like y equals log of x base 3, then what this truly means is that 3 to the y power is equal to x. So a logarithmic expression can be rewritten as an exponential expression, as we saw yesterday. And an exponential expression is something we've already graphed before, right? And the magic numbers we got for an exponential expression for the powers were negative 1, 0, and 1, because those were easy. But now the power is y. So typically we pick x's to solve for y. In this case, we're going to pick y's to solve for x. So if I pick y equals negative 1, 0, and 1, 3 to the negative first power is 1/3. 0.33 is a decimal. 3 to the 0 power is 1, because anything to the 0 power is 1. And 3 to the first power is 3. And if you want a quick verification here, these two are easily verified. Log of 3 base 3, of course, is 1, and log of 1 base 3 equals 0. You can see those are both true. And trust me, the log of 0.33 base 3 is negative 1 approximately. All right, so once I get my points, 0.33 comma negative 1, I've got 1, 0, and 3, 1. That gets me 3 points on the graph. And with the exponential graph, we always expect that curve, right? So we're expecting that bend to happen right there, like so. One side goes to infinity, the other side is going to level off. And what I want you to realize this is no matter how big I make y negative, negative 2, negative 3, negative 4, negative 5, and so on, 3 to the y power cannot be less than 0. Okay, all that, like if I do 3 to the negative 17th power, that's just 1 over 3 to the 17th power. It's still positive. It's very, very close to 0. So what I need you to see here is that this graph, although it's going to go down, it's never ever going to reach x equals 0. So I'm going to go like that, and we're going to put a vertical asymptote in to represent the fact that it's not going to cross that y-axis. On the other side, if I wanted to go bigger, let's say the second power, 3 to the second power equals 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, comma 2. And that's the next point. So you got your bend, got your bend happening here. It's rising gradually. Okay, a logarithmic graph looks like an exponential graph. It's just been turned sideways because logarithms are inverses of exponential functions. So that creates an inverse function look to it. But it still has an asymptote, still has this rule about it can't cross a certain point. And getting into our next topic, which is domain, what I want you to understand about logarithms is this. Log of 0, base anything, is undefined. Because again, log of 0 base anything means that something to a power is equal to 0, which is not possible. Okay, something to a power can get close to 0 but never equal to 0. That's undefined. And for that matter, also log of a negative number base anything is also undefined. So anytime we deal with a logarithm based on its domain, there's going to be this vertical asymptote based on its domain, because there's going to be a spot where that graph's not allowed to cross. And depending on signs, it could be flipped up this way, it could be flipped back that way, whatever. Signs can make things change and stuff. And if you're doing x plus 1, that can move it backwards. X minus 1 moves it forward, stuff like that. So it doesn't always happen at 0. But there's always a spot where 0 is going to happen or a negative number is going to happen. The graph has to happen on the positive side of the asymptote. So asymptote's here at 0. Every value of x being positive would be over here. That's where the graph's going to be occurring for this logarithmic graph. Again, for now, I would say to do logarithms, I would simply make it an exponential function, graph it as an exponential, choose y, solve for x, plot the points, x, y order still, connect the dots, and have an understanding what the graph should look like to help you graph it properly.